Here, we want to look at a special technique in circuit analysis. It's called mesh analysis. Mesh analysis itself is the application of KCL and KVL. So let's look at this example. In this example, you can see all the current passing through the resistor, they are unknown. So mesh analysis is used to find this unknown current passing through the resistor. So the aim of the mesh analysis is to find the unknown current. And the method it employs is KVL. So first look at it, how we set up the question. 1. Assign mesh current I1, I2 clockwise. Now, again, it doesn't matter. It doesn't matter clockwise or anti-clockwise. So we can keep this one in clockwise. This is mesh current 1. We call it I1. This is mesh current 2. We call it I2. Now remember, the mesh current is flowing within the mesh or the loop. So there are two loops, the left loop and the right loop. Each loop has its own mesh current. Now this mesh current doesn't have to be the wheel current. So you can imagine mesh current like a tool. So they are not necessarily corresponding to the wheel current. It could be, but it also may not be. So we'll see it now. Next, we want to write the KVL for each mesh in terms of I1 and I2. For the left hand side, we have mesh current I1. Now we will use the procedures which electrical and electronic engineers they will use. First, let's look at the current I1. Now you can see the mesh current I1 enter the source from the negative side. So we'll say this voltage is minus 10. Next, the current now parallel passing through R1. So I1, R1. So if we ask what is the potential difference across R1, we can apply Ohm's law, which is equal to R1, I1. Therefore, I will put here R1 is 1K multiply I1. Remember, this is the potential difference across R1. Now let's look at the case of R3. I1 passes through R3 from top to bottom. However, R3 also share by the right hand side loop. So, and this loop has I2, which is going from bottom to the top. I2. Because from the point of view of I1, it means from I1 point of view, this current must pass through from the top to bottom. So we can assume one thing, which is I1 is bigger than I2 from the point of view of I1. It means the total current passing through R3, it should be I1 minus I2. The difference, because I2 is opposite to I1. Now, what is the potential difference across R3? Multiply 1K. So this is the potential difference. Now, let's look at the left hand side loop, and we can say we have minus 10, we have 1k I1, and also we have I1 minus I2 1k. So the sum of these three terms must equal to 0. This is what the KVL says. The first equation, which on the left side of the loop or the mesh is minus 10 positive 1k I1 positive 1k I1 minus I2 and equal to 0. Again, you can see I drop the unit, but I make sure I keep the prefix. It means k, in this case, is the prefix, mean 10 to the power 3. The next equation comes from the right hand side. From the right hand side, we'll see again, this is the negative, this is positive. So I2 enter E2 from the negative side, so this must be minus 20. I2 also passes through R2, so the potential difference across R2 due to I2 is equal to 2k multiply I2. This is the potential difference. We already applied Ohm's law. For the R3, the situation will be reversed because we are analyzing from the I2 point of view. So we must, in this case, assume I2 bigger than I1. So we can pass through the I2 through the R3. So again, this is just the rule. At the end of the day, what is the current? We'll find out later. So we'll say from the I2 point of view, the current passing through R3 is I2 minus I1. We have to assume this time on the right hand side, I2 is bigger. And the resistance of R3 is 1k. So this is the potential difference across R3 from the point of view of I2. Again, we have three terms, and the sum of these three terms must equal to 0. This is what KVL say. Let's write it down. Minus 20 plus 2k I2 plus 1k I2 minus I1, and this is equal to 0. Now I can call this equation 1, equation 2. Next, I will tidy up equation 1 and equation 2. And you can see here, I collect the term I1, I2, and then I also see this is a constant. So I move the constant to the other side. Once I tidy up, equation 1 will become 2k I1 minus 1k I2 equal to 10. This is equation 3. It will be minus k I1 plus 3k I2 equal to 20. Now, in this case, you can see we have two equations and two unknowns, I1 and I2. So you can apply whatever method you know to solve I1 and I2. For example, you may know matrix, so I can say 2k minus k minus 1k plus 3k I1, I2 equal to 10, 20. And then you can use determinant to find the solution. Of course, you can use substitution and elimination to find the solution. Let's use elimination to find the solution. I will say 3 plus 2 times 4. 2 times 4. Now you can add these two equations. This is 0, and you get here 5k, I2 and 50. So I2 equal to 50 over 5k. 50 over 5 is 10. 1 over k is milli. So it's a 10 milliampere. Now I put the A in the final stage. Next, we want to find I1. So we substitute I2 into 3. So 2k I1 minus 1k. This is 10 amp equal to 10. Again, k amp, they multiply equal to 1. So you got 2k I1 minus 10 equal to 10. And from here, I1 equal to 10 milliamp again. So just highlight I2 10 milliamp, I1 10 milliamp. In this particular case, they are equal. So we assume I1 flow in the left side of the loop clockwise. So this is I1, this is 10, this is I1, so this is also 10 milliamp, and I1 passing down R3 from top to bottom. This is also 10 MA. I2 of the right hand side also flowing within the loop clockwise. So this is 10 MA. Now here it goes up 10 MA, and here 10 MA. So you can see the I1 on the left hand side and the I2 on the right hand side. In this particular case, they cancel out. So there's no current passing through R3. Let's calculate the potential difference across R1 and R2. The potential difference is the current multiplied the resistance. So 10 amp multiply 1k. So therefore you get 10 volt. Same, 10 amp multiply 2k, you get 20 volt. Now let's analyze the voltage at this circuit. This is negative. We can assume this point is ground. It means it's 0. Now this is 0, and then the E1 voltage source is 10 volt higher. So this point here should be 10 volt. R1, the potential difference is 10 volt, and the current flow from the left to the right. So in terms of potential, this is high, this is low. So this must be 10 minus 10. This point must be 0 volt. Now this is important. This is 0 volt, and also this is 0 volt. Therefore, there's a no potential difference between R3. There's a no current flow. How about here? How to reconcile this 20 volt? Because we force this part as 0 volt, so this will be forced as 0 volt. But the voltage source just say this is high, the other side is low, and how much lower is 20 volt. So this point will be minus 20 volt in this case. And this is consistent Why? Because if you look at this point here, 0 volt, this minus 20 volt, and this is high, this is low, and the potential difference across R2 is 20 volt. So the current flow from high to low. So everything, they're all consistent. As a practice, let's apply mesh analysis on this question. We follow the procedure. 1. Assign mesh current I1 and I2. So this is number 1, I1, I2. Number 2, write the KVL for each mesh. Again, I1 passes through E1 from the negative side. So this is negative 15. I1 passes through R1. So I1 is here. So the potential difference across R1 is 1K, the resistance, multiply I1 by Ohm's law. R3, I1 passes down, and the other side we have I2 going up. So for the I1, we have to push it from the top to bottom. So the current will be I1 minus I2. And the resistance is 2K. So we got 2K. And this is the potential difference across R3 from the I1 mesh. So the first equation will be minus 15 plus 1K I1 plus 2K I1 minus I2 equal to 0. The right hand side loop, this is negative, this is positive. So when I2 passes through E2, this is negative 5. And this is 1K multiply the current I2. This is the potential difference across R2. From the point of view of I2, I2 must be bigger than I1. It means this time I2 must be bigger than I1. So the current from the point of view of I2 is I2 minus I1. This current multiplied 2K is the potential difference of R3. So now we have 3 terms. We can write it down. Minus 5 positive 1K I2 positive 2K I2 minus I1 equal to 0, 1, and 2. So now we tidy up this one. From 1, we can see this is equal to 3K I1 minus 2K I2 equal to 15. This is 3. From number 2, this is minus 2K I1 plus 3K I2 equal to 5. So this is 4. Again, we can use whatever method to find I1 and I2. Now, if we use elimination, we can say 3 times 2 plus 4 times 3. So the first term, I1 term, eliminate. The second term, we will have minus 4K 3 9K I2. This is 30 plus 15. So we will have 5K I2 45. So I2 equal to 9 milliamp. Substitute I2 into 3 and you will find I1 equal to 11 milliamp. So with KCL we find I1 equal to 11 milliamp, I2 equal to 9 milliamp. So let's mark this current on the diagram. So I1 11 milliamp. This is clockwise loop. So this is I1 again, 11 milliamp. On the left hand side, this is 11 milliamp. Now I2 again, clockwise. That's what our assumption. This is 9 milliamp. This is 9 milliamp. And also this is 9 milliamp. Now you can see here 11 milliamp from top to bottom is larger than 9 milliamp from bottom to top. So overall we can say this is 2 milliamp from top to bottom. So the correct here is 2 milliamp from top to bottom. Now let's look at the potential here. Assume again the bottom part here is 0 volt. So we have 0 volt here, and E1 will rise 0 volt to 15. So this one here must be 15 volt. Now the potential difference across R1 is 1K multiplied 11 milliamp, so it's 11 volt. And this is high, this is low. So it means this one must be 15 minus 11, so this is 4 volt here. Now let's look at the R3, 4 volt, 0 volt, so 2K multiplied 2M equal to 4 volt, so this is consistent. How about the E2? E2 is 5 volt, but because we force this one at 0, so all the 9 here, they are 0 volt. So this also 0 volt. It means you have to force the other side as minus 5 volt. And if you look at here, this is positive 4, minus 5. So the potential difference is 9 volts. And if you look at 9 milliamp, 1K, so the potential difference is 9 volt. Again, this is consistent. Here, we want to look at the second special method in circuit analysis. It's called nodal analysis. In this technique, the main purpose is find the voltage in the circuits, and the way it do it is to use KCL method. So how to use KCL method to find the voltage? Let's do it. You can see in this example, there's a several nodes. This is one office we call A. Now we can call this one C. There's another not so obvious. This is B. Now this B is not the usual sense of node, because usually we think node as 3 branches, 1, 2, 3. But in this particular case, I can call this one node because it's the connection between R3 and R2. So another important point is find the reference ground node. So I will use C as our reference. So if I use this one as ground, so the potential here VC must equal to 0. So this is 0, this is 0. Number 2, label unknown node voltage V1 and V2. Okay, so this is V1 and this is V2. I put it here A and this is B. Number 3, write the KCL at each non-reference node. And 4, express all current in terms of the node voltage and resistance. This one here is IS. We can assume at node A, IS will split into two paths. And one is I1 and the other is I2. When the I2 passes R3, it reaches node V2. When the I2 passes R3, it reaches the node B. And we can assume here this is I3. Of course, we know I2 must equal to I3, but we just put it here. This will be enough for this particular case. So write down the KCL. So KCL at A, which is equal to IS, the current in, equal to the current out. Now we want to express this one in terms of the voltage and the resistance. What I mean, IS remains unchanged, but I1, if you look at I1, this is the voltage. So this is also I1. I1 will passing through the R1 as well. Remember, this point here, they should have the same voltage. So this is also V1 and this is 0. So if you look at here, the potential difference across R1 is V1. So I1 should equal to V1 over R1 plus I2. I2 here, if you see, this is from high to load. So the potential difference is V1 minus V2. So V1 minus V2 divide R3. So R3. So this is our first equation, and this equation will be 2m equal to V1. R1 is 1k plus V1 minus V2, and this is 1k. Equation 1. Next, look at KCL at B. The B here has one in, one out. So I2 must equal to I3. I2 can be expressed as the difference between V1 and V2 divided by R3. I3, if you look at here, I3, but the potential difference across R2 is V2. So I3 must equal to V2 over R2. So let's plug the number in, and this is V1 minus V2 divided by R3. R3 is 1K. And then V2 divided by 2K. So you can see we have two equations. So as an example, I would like to solve the equations for you. So we can say from equation 1, if we multiply both sides by 1K, it means we multiply here 1K, we multiply both sides by 1K, and you'll get a much cleaner equation. This is become 2, and this become V1 plus V1 minus V2, or I tidy up again, 2V1 minus V2 equal to 2. So this is equation 3. From 2, this time I multiply both sides by 2K, and you will get a 2 V1 minus V2 equal to V2. So 2V1 minus 3V2 equal to 0. Number 4. Now solve these equations. It's very easy, and you will find V1 equal to 1.5 volts and V2 equal to 1.0 volts. Now we must check everything whether they are consistent or not. So let's check all the steps. Solve simultaneous equation. Yep. Compute the current through R3 and indicate its direction. Check KCL hold at V1 and sum. Okay, let's do it. We found V1, this is at this point, equal to 1.5 volt, and V2 at this point equal to 1.0 volt, and we assume the ground here is 0 volt. So the current passing through R1, which is our assumption I1 must equal to 1.5 volt over 1K ohm, so it's equal to 1.5 mA. So this is 1.5 mA, and here the potential difference between R3 is 0.5 volt. Divide this one by 1K ohm, so you got 0.5 mA, so 0.5 mA. So you can see the sum at A is equal to 1.5 plus 0.5, and it is equal to 2 milliamp. And also it must be consistent. Why? Because this is 1 volt, this is 0 volt. So the current passing through here is 1 over 2K. So it's a 1 volt over 2K, and again it's 0.5 milliamp. And this is I3, and I2 and I3, they are equal, of course. They are along the same path. So everything, they are consistent. Let's look at this practice. 1. We are going to use nodal analyze. So we label V1 and V2 relative to the ground. So we have to select where is the ground. This is the ground, 0. and this is one point here. We call the A, the other point B. So we call this one V1 voltage. This is V2 voltage. Okay, now let's put down the KCL at A. So the KCL at A, there will be different current. So this is our IS, and we can assume we have I3 flowing here. For the other path, B, we can see the IS flowing into here, and the I3 will flow into B, I3. So this will be I2, and this is 0, and we can assume there is a current flowing from I1 down here as well. Now remember, sometimes we have to make an assumption, and this assumption may not be followed intuitive. However, we'll find out by the sign. So we just make this assumption here. So KCL at A, in this assumption, there's a no in. They're all equal to out. I1 plus I3 plus IS. And I1 is the current passing through R1. So the potential difference is V1 over 0. So it's V1 over 1K. I3, assume I3 flowing to here. So the potential here is V1, and this is V2. So it means the potential difference is V1 minus V2 across R3. So I3 can be written as V1 minus V2 divided by R3, 2K, plus this is 1M. So this is our first equation at B. Okay, so at B we have 2 in, 1 out. So the in is, this is out, IS is 1M, I3 here. Now I3 we already assume, and we already know this is V1 minus V2 over 2K. And I2 is, so this is V2, so I2 equal to V2 over 2K. This is equation 2. Again, we can simplify this one. Say, for example, we multiply 2K on both sides of 1. We arrange this one, of course, and we'll get 2V1 plus V1 minus V2 multiply 2. 2K multiply 1M is 2, equal to 0. And this is 3V1 minus V2 equal to minus 2. So this is equation 3. Now 2 multiply 2K again. And this is V2 plus V1 minus V2 equal to V2. So V1 minus 2V2 equal to minus 2. This is 4. Now we solve equation 3 and 4, and you should get V1 equal to minus 0.4 volt and V2 equal to 0.8 volt. Let's analyze this circuit with the value of V1 and V2 we found. This is A, and we found this V1, and V1 we found is minus 0.4 volt. So this is minus 0.4 volt. B, we found it is equal to 0.8 volt. This is our V2. And this is our V1. Okay, let's look at the current passing through R3. V2 is higher than V1 actually. So the potential difference is, this is 0.8 volt, this is minus 0.4 volt. So the difference here is 1.2 volt. So the current passing through R3 should point to this direction. So this is the real current, and this current should equal to 1.2 divided by 2K. So this is equal to 0.6 milliamp. So this is 0.6 milliamp. And because here we assume this is 0, and now the current actually flowing from the 0 to V1 in the opposite direction. So this one will be 0.4 divided by 1K. So this is 0.4 milliamp. So now if you look at this one here, it makes sense because 0.6 milliamp going in to the A here is at 0.4 going in, and then it go out here, and the sum is exactly 1 milliamp. This is IS. This is 1 milliamp, and this one is 0.6 milliamp. Now let's calculate the current passing through R2. The current should be 0.8 divided by 2K. So 0.8 divided by 2K ohm, of course. And you will find this one is 0.4 milliamp. Again, this is consistent because now we have IS, which is 1 milliamp flowing in to the B, and 0.6 flowing out, 0.4 flowing out. So the solution V1 and V2 will give a consistent current passing through the circuit.